to start with continuing with Professor Miguel on the second day of our mini course, and things are getting more and more exciting. I heard a lot of excitement yesterday. Today is going to be even more fun. That's what I heard.
Thank you very much. So today is going to be probably even more intense than yesterday. I will start first with a brief recap of what are the main things that we have learned yesterday, and today we will use them in many possible ways. Okay. So
yeah, do you mind just hiding this?
Yes. So yesterday we started with the idea of linear transform in general in a discrete world. We had a vector which was, say, of dimension ns, and somehow we mapped this into a vector which was of dimension nb. Okay, this was the number of basis elements, and you did an exercise. So we wrote this as the problem of solving a linear system of this kind, and we saw that there can be different scenarios. The system might have a solution, no solution, infinite solutions, and we saw that we will stick mostly to the least square flavor of the problem, which is the case where you don't have an exact solution, but you just project your data into a basis. So here the matrix B is the matrix that contains along its columns the basis, okay, until NB. Then there are various special cases. We saw in particularly interesting one is when the basis is orthonormal. In this case, this is identity, and so going back and forth is very easy. We saw then the case where NB is equal to NS, that's for instance in Fourier, and then in this case you can go back and forth without losing any information. But in the most general case, we will be in a situation where NB is usually smaller, or very rarely it will be equal to NS. So we are accepting some losses of information, okay? We saw this for one vector. And then we discussed the case where you don't have just one vector, you have many vectors that are potentially linked according to some dynamics, okay? According to some dynamical system. So in the second part of the lecture, we move to a case where, as I said, we have a snapshot matrix D that contains now not just one vector like in this case, but many. We were calling it D, so D1, D2, and so on, until NT, and this matrix is of size NS times NT. So we picture this matrix as containing snapshots along each column. For example, it can be a velocity field, it can be images, it can be whatever you are trying to decompose, and you have collect NT of them. So every column is one snapshot of your data set, and every row is a time series that tells you how the data has been evolving in time. Okay. So we picture this as as if you want, as the discrete sampling of a function which depends on space and time. Okay. And I'm going to assume that the sampling is uniform. It's not really necessary. There are ways in which, I mean, releasing this assumption will cost us maybe 20 more minutes of class. But so for the moment, I'm going to keep this assumption. So time is going to be sampled uniformly as, say, K delta T. And space is somehow sampled uniformly as, let's say, I delta X, where this I has to be a matrix linear index, because we assume that somehow you had a vector field or an image or whatever, and you have reshuffled it into a vector. And depending on how you've done that, this index I will span various elements of your data set. But you get the picture, so I'm not going to go more into details on this one. And what were we interested in doing here? We wanted to have a decomposition of the form sum of a decomposition. This is a matrix. We want to decompose as a summation of matrices which we were writing it in this way. So you sum from 1 until R. I will say a bit more about this R in a few minutes. So you have a composition of what we will call modes. Each of these is a rank 1 approximation of our matrix D. This is a set of basis vector like we built here, but for the space. This is a set of basis vector again as we built here, but for the rows. That's why we play with this transposition here. So this is, say, a vector of dimension ns times 1. This, because of the transposition, is 1 times nt. So each of these guys is ns times nt, like the original one. Why are we interested in that? We saw 4 good reasons yesterday. Today you will hopefully play with one of them in more details. We also saw that this can be written as a matrix factorization of the form phi sigma psi transpose, where this is the matrix, the equivalent of B, if you want, containing the spatial basis. This is the equivalent of B, if you want, but containing these spaces. Transpose because I wanted to act on the rows. And this is a diagonal matrix that contains all the sigmas. Then we saw many of you might have thought, well, this is just an SVD. The SVD is one case of that, which is also the case that we will see today. Okay, this was all clear. Now, because this is a diagonal matrix, I think this is the main point here. Because this is a diagonal matrix, you are not free to choose both this matrix and this matrix. One, you're choosing one of them, the other comes through a normalization. If I release the constraint that this is a diagonal matrix, then I enter in the world of 2D decomposition. For instance, I can do 2D FFT. If I do a 2D FFT, I'm saying that this is Fourier, and this will be the 2D transformed Fourier. Or if I do 2D wavelets, this could be wavelets, this could be wavelets, and then this is the 2D wavelet transform. Okay, so in that case, of course, everything works just fine, but this is not diagonal, which is what we want to achieve the variable separation that you have also seen in PDEs and in other problems. Okay, so how do we get? You can go in 2 ways, either by rows or by column. I can tell you, I give you phi, and then you compute the rest normalization, or I give you psi, and then you compute the rest through normalization. Okay. Now the general formalism, I continue to be here. If we have B equal this, in the same way we had a very general formalism here for the autoencoder, we can build a very general approach to the 2 ways of encoding that. So look first for phi, look first for psi. So for example, let's assume approach 1 is that I gave you this. And that's what we saw yesterday with Fourier. In that case, I want to find this back. Normally, because this is diagonal, I can regroup them somehow together, right? This, if you want, would be the encoding with respect to this basic. Maybe let's write it like that. Is the encoding with respect to this guy, which will have its own associated phi, right? So if I give you this, so let's say this is given, then you just multiply on that side by the conjugate of the matrix. What you have is this. If your matrix is orthonormal, like in the case of Fourier, you're done because this is dead. But if it is not, then you have to move this on the other side. And so you will arrive at this situation. And then we saw how to normalize this to find the basis and the sigmas, okay? Or I might tell you, no, I don't want to work like this. I give you this instead. It's the same idea. So now you will hit this problem on that side. So for instance, you start by multiplying by this transpose. Again, if this is orthonormal, you're done. If it is not, you need to do a little extra work. And then here again, you have to play with the normalization, but be careful that we have the transposition, so we might just have them to transpose the result. But we can do also that, okay? Is this clear? Do you have questions on that? So every time I want to tell you, I'm going to introduce a new decomposition. Either I tell you one way to compute that or one way to compute that. Okay. Now we will see the PCA or the proper orthogonal decomposition. This I can erase. Everything is clear. Yes. So when we go, the menu is as follows. I would like first to introduce the general idea of the POD, PCA. Then I will show you some algorithms. There are many algorithms, and I gave you in the Python file many ways to compute that. And there is a comparison both in terms of computational cost and accuracy and so on. And I want to go very fast on these first two items, because then I want you to play a bit with the Galerkin projection, which I understood that it's of interest to many of you. Okay, so I'm not going to go through all the slides, because the slides go into more details than what I will cover here. So, plus you are all familiar with SVD, no? Who does not know what the SVD is? Okay, so we will briefly review it. Now, the idea for the POD PCA is that whether I take any of these two approaches, if I take this matrix to be NT, and this one to be NS, so complete basis, let's say, I could potentially reconstruct the whole thing. I could build a lossless approximation. But if I decide that I will truncate this, for example, I'm going to pick only the first 5 modes or the first 6 modes or something like that, then we're going to lose some information, precisely because of what we saw yesterday, okay? There's no hope that we're going to keep all the information. So let me define as V tilde, say phi tilde R, sigma tilde R, psi tilde R. Let this be a truncated approximation. So when we've picked only R modes, okay, maybe, yeah, let me put a big, not to confuse with the indices. So somehow now we are summing from 1 to R, where R is smaller than what you need to have the good approximation. I will say a few more words about R soon, okay? So we are truncating this. And so we know we are going to make an error. And now what I want to have is that the error which I obtain in doing this, so let me put an R here also to say that this is truncated with R modes. I want this error to be the smallest possible. The minimal error that you can have. Pick phi or psi, again, you cannot pick both. So remember this, pick one of them in such a way that for every R, up to the last R that you can take, which again I will comment in a few minutes, for every R, we want to have the best possible approximation. Okay, so this becomes an optimization problem, a constraint optimization problem. Why constraint? Because we will always demand that the length of this guy is unitary. It makes our life much easier, because then it means that the sigma will be the only responsible to say whether that mode is important or not important. All the energy is in the sigma. It's not a bit in the sigma, a bit in the phi, a bit in the psi. So if I impose that all these guys have unitary length, and the same also for that, and I solve that minimization problem, which is what the detail in the slides, but I will skip all of it. I arrive at a very precise condition for the size or the phi. Again, I don't have to constrain both, right? So I give you directly the solution, and then we serve through the slide for you to see how this solution was derived. The solution is that For the phi's, what you know is that they should be eigenvectors of this matrix, which in statistics plays a big role. It's a very important matrix. No problem. Maybe I will not spoil too much, and I will just put eigenvalues there. Okay. Concerning the size, instead, they have to be eigenvectors of this one. Okay. And the beauty of this symmetry is the fact that the eigenvalues of these two matrices will be shared, will be the same. The non-zero eigenvalues will be the same. And moreover, they will be linked to the sigma, which we have seen before. Okay, so in both cases, I can write this. Per se, it's a big news because it means that you don't need to rescale and to renormalize. You will already have the sigmas served for you. Okay. The other beautiful property. Can you tell me one big property of the eigenvectors of this matrix or this matrix? No, the eigenvectors, you have diagonalized it, but the eigenvectors have a special property. In fact, when you write the eigenvalue decomposition, I was not allowed. I mean, in principle, I should write it like that, right? If I am allowing myself the luxury of writing that, is because yes. Okay. Because this matrix is symmetric positive, at least semi-positive. I mean, the eigenvectors of the eigenvalues of that will not be negative. It's like the square of the matrix. It could be zero if the matrix is rank division, but they give orthogonal eigenvectors. Both of them are orthogonal.
Miguel,
Yes.
I'm sorry to interrupt. On Zoom, we only see the table of contents and none of your computations. Are you writing down somewhere this computation you are talking about?
They are on the blackboard.
Can't we have the blackboard on Zoom and not just the table of contents?
Maybe we can attempt, but zoom in to the whiteboard. Oh, no, the problem is not in the camera. We see the mirror, but I think we can attempt to zoom in.
Do it if it is easy. I don't want to interrupt the lecture.
Okay, so I'll call in Hiba. She's
Okay. Okay, thank you. Thank you, Sarah.
We are working on that. Hello, Michael. Happy to know that you're there.
Uh-huh.
Happy to know that you're there.
I am, and listening to you. Go on. I'm able to understand, you know, but I think other people cannot understand if they don't see your computations.
I think, Mikhail, can you tell us if you can now report seeing the SVD decomposition?
Okay. For the time being, I see just a table of contents. When I see something else, I'll tell you.
At the camera.
Okay, you have to look at the speaker, not the slides. So there are two views.
The speaker is something like 10 millimeters to 20 millimeters. It's very hot.
Okay, then. Yeah, you can pin the speaker so that you see his view.
No way. I tried.
All right.
I tried. No way.
A picture and send it your way on WhatsApp. So that's how I'm gonna work it out this way. I'll take a picture of the whiteboard and send it to you.
Oh, why not? Thank you. This is so kind.
So because this is this is going to be the only decomposition that gives you orthogonality both in the spatial structures and in the temporal structure, which means that both these approaches are going to be significantly simplified. Okay, this identity, and also this you don't need this identity. Okay, So
I have a small question.
Yes.
Isn't in general the eigen decomposition of any matrix or should be orthogonal, or there's, I'm not sure.
is any the
Isn't a rule that when the eigenvectors of matrix are always orthogonal?
no. Generally, you don't have orthogonal eigenvectors. The matrix has to respect some properties to give you that. Each matrix respects those properties.
The eigenvalues are distinct.
So, what is in the slides? In the slides, you have a quick recap of constrained minimization or maximization, and you have the derivation that takes you there. Okay, it starts by, for example, from the left-hand side, so from that. And if you follow the derivation, you arrive at the solution. So sorry for this one. You arrive at the solution that the psi's have to respect this condition. Okay. I want to go fast on that because I want you to go to Python very soon. But so just follow these steps, and you should be able to arrive at this result. Now the main there is a nice paper from Aubrey in 91 who celebrates a bit this beautiful symmetry of this decomposition, which in fluid mechanics was called POD. So we landed in the proper orthogonal decomposition. But as I was saying yesterday, the POD is, you should see it as a more general concept than just the SVD. Okay, the SVD and POD are perfectly equivalent if we use the inner product that we have used so far. Okay, but in the case, for instance, where your sampling is not uniform and you have to introduce weighted inner product, or you want to do the integration for the inner products in a more sophisticated way, then we will depart from the SVD. Okay. So, but for all the simplifying cases, these are some references. For all the simplifying cases that we have mentioned, we will land into the SVD. Now, in how many ways can you compute the SVD? In Python, I count approximately 10. Okay, and I give you in the code, there is one code that tests all of them. The first big distinction to make, and historically it was the split in between what is called the classic POD and the snapshot POD, is whether you want to work with this guy first, compute the phi's, and then complete your process from here, or compute first this one, and then use this one to complete the problem. Okay. What is the distinction? So, I mean, what is the dimension of this matrix? Yes, this is NS by NS. And this one? NT by NT. So how do you choose whether you want one or the other? It depends if you have more snapshots or if your snapshots are much bigger. So in one case or the other, you will first work with this approach, compute the eigenvalue decomposition, then project, which is very easy. So it's a simplified version of that. Or you work first with this and then you project. Okay. Now, normally, if you look at a modern SVD implementation in SciPy or NumPy, it usually does it without you having to tell which path is better. Okay, so you can either implement it in this way and use various kinds of eigenvalue solvers for that, or in this way and use various kinds of eigenvalue solvers, or directly run an SVD. Usually the SVD tends to be more memory demanding, unless you have a special case of SVD. We use the so-called randomized approach. So I gave you a code, which unfortunately will not have the time to serve too much into detail, which is called one POD in 3 ways, because in fact there are many more ways in which it is computed. One is using the PCA. Yesterday we were discussing about the distinction with PCA. In scikit-learn, you have very efficient implementation of the PCA, which is in fact is a wrapper to Fortran. So this one goes very, very fast. And here you see how you will convert the result of your PCA into our view of phi, sigma, and psi. Okay. And here you have a little code to test how much memory has been used and how much time it took to do the computation. This is probably the fastest among all the algorithms. There's one reason why I don't usually use this, is because this algorithm by default removes the mean of the data set, which is something that I usually don't like to do unless your data set is fully stationary, and it has, in fact, a mean. Okay? When I say remove the mean, I mean that taking your matrix D, where you have all your snapshots like that, it will compute the mean flow, so the mean field, so the mean by rows. It will give me the average snapshot, and will remove the average snapshot from all the columns. This is by default going to be done by PCA. Okay. And then I'm giving you various options. So this one is, for instance, calling the SVD from NumPy. This is the most accurate one, but also the most memory demanding one. It will automatically compute all the singular values and all the things that are there. And then if you use Modulo, in Modulo you have various options, which are all wrappers to SciPy functions or NumPy functions. Among one, the fastest is this one, which is using the SVD randomized algorithm. This is orders of magnitude faster than this one and uses much less memory than the other ones, but it tends to lose accuracy if you go towards higher modes. So if you want to evaluate more sigmas. So if you're looking for, say, the 5 leading POD modes, then this could be a good option. If you want to look at all of them, then this is not a good idea. Okay, you have one approach which is called compute POD SVD, which will compute the POD through the SVD, and there you can choose among various SVD solvers, or you can do here it's called compute POD K, which will compute the POD from this one. Okay, I forgot to mention that these matrices I usually call them K, and this one I usually call it C. As I said, they are very, very important meaning. Okay, this one is telling you, if you picture it, let me maybe I show you briefly this. If you picture that matrix, this one we don't need anymore, right? This is very clear. So if D, so let's picture D transpose D. What is that? You have D, which has been transposed, so all your snapshots are in this way, times all your snapshots in the original position. So each entry is just going to take the inner product in space between two different snapshots. Okay, so here K, let's say EJ, will be the inner product of the snapshot DI with the snapshot DJ, and this is an inner product taken in space, okay, with the whole snapshot. And you can show that this one, which would be the transpose, I mean, you will go by row, it will do the same, but for the time series. Okay, so from here you have that the CIJ will be, it will be now an inner product in time, so this is in space, where this is in time. And now here you will look at the notation which we were using yesterday was DI, and then here you put DK, sorry, and this will be DJ DK. So this is the correlation of any pair of time series in your data. This is the correlation of any pair of snapshots in your data. Okay. Now, since I want to go quickly to the exercise on the Galerkin projection, I jump on the main idea and then you do the exercise, okay? So the main idea is the following. Let's say that you have a dynamical system that can be nonlinear and it's advancing in time according to some complicated function. Let's say that you have been given some data. And from that data, you compute your POD decomposition. So you now write your variable as a linear combination of some modes. these coefficients, so you have your spatial basis and then you have your temporal guys, which will be sigma times psi. But here I don't need to make this distinction of the sigma, okay? The sigmas for this application are only important to decide how many modes you will use, but then you will let the equation tell you what should be the psi's associated to that, okay? So we use the sigma to say 3 modes is enough, okay? Then you will truncate these to 3 modes and you plug it into your equation, okay? This is what we will do right now. What happens is something like that. So I've plugged all my summation inside this guy. If this is a nonlinear operator, we might end up with something really ugly. But on the left-hand side, we have that the time derivative is eating only on the time coefficients and not on these guys. And we said that these are orthonormal. Okay. So if now we take the inner product with respect to, say, the basis number 3, here, only one guy will survive, which is the one that has the basis number 3. All the others will die. And when you do this projection, here you will end up with a system that might, again, look ugly, but you will see in the exercise that I gave you, it does not really look too ugly. But if I have, say, 3 modes, I have obtained now 3 equations for the 3 coefficients. So I have an ODE of dimension 3. Okay? Is this clear? So I will ask you to open the file. There is the file exercise session 3 to Galerkin to give, and we will go through this exercise. Okay. There is also another one which is about the POD of the cylinder, but maybe we check this after the break very quickly. Let's give the priority to the Galerkin problem. So what do you see in this? So I skip this and I go here. So what is the exercise? The exercise is the following. We have a pulsating Poisson flow, which has been already written in dimensionless form. Sorry, I think I messed up with the second screen. Okay, so we have a pulsating Poisson flow. We come back to this later, as I said. Yeah, we have a pulsating Poisson flow. So you have a channel, 2D channel, okay, where you have a flow that is fully developed. And now in this channel, the pressure gradient that is driving the flow is pulsating, like in your veins, for example, okay? And because of this pulsation, the velocity profile will pulsate, okay? Under some assumption, which I will skip, you arrive at simplified Navier-Stokes equation into this problem, which is a parabolic PDE, which depends in time. And the pressure gradient here, we will pick it as an harmonic, very regular frequency, say like in your vein also. If you scale down this equation, that's a beautiful exercise in scaling analysis, you arrive at deriving the dimensionless form of this problem, which will depend on 2 dimensionless numbers. In fact, only one, because the ratio is what matters, but there will be one big dimensional number, important dimensional number, which is the Womercy number, okay, which is weighting how important is the time derivative here. And then you have this dimensionless p hat, which is telling you how strong is this pulsation, okay? So at the limit for this guy to go to 0, you will be in quasi-steady, and so this term will be irrelevant. And in fact, this will be, you will have the steady state solution, so the parabolic profile that will pulsate. But if this guy tends to be larger, then your velocity profile will no longer be parabolic. We'll have some wiggle. So you see it in the exercise which I picked. So the shape of this profile will be strange. This is associated to some loss of energy.
The view is somewhat messed up on Zoom, so we see it.
You see the black one.
Yeah, I think I'll show you. That's what.
Ah, yes. So okay. So I do stop share, and then I reshare, and I go like this. Better.
I think here is okay. I have to just check with.
Normally now I'm sharing
Yeah, I
the
think
screen.
no.
So is it clear what this solution will look like? Now, this has an analytical solution, which I provided you in the beginning of the code. And the analytic solution is something that looks like this. You have an expansion of in eigenfunctions of the problem, which are cosine functions. And in the first part of the code, you will see that you can put this. We will pick p hat 60 and w10, which is also not too far from what happens in your veins, by the way. And from that, you can build the analytic solution using 20 eigenfunctions. Okay. Then I ask you to solve it through finite differences. We will compute the POD modes of that. We will see that 3 modes are largely sufficient for this problem. We will project our problem into these 3 POD modes, and we will obtain a much easier dynamical system. Okay. So do you have this file in front of you? I will have to go fast on the first part, but on the second, I would like you to do it with some more details, okay? So to do this. So you have this file in front of you. Let's go quickly through it. There is the one that is to give, which will throw an error at some point. So in the first part, we are creating the analytic solution. And guess what? The analytic solution also has a spatial basis, an amplitude, and a temporal basis. So I am reshaping this in the same form that we have used, that we've been looking for, okay? So as a product of 3 matrices, which I think in the code I called Y, A, and Tn. Okay, so you have your data is going to be capital Y times A times T, where this plays the role of psi, this plays the role of sigma, and this plays the role of phi. But you have an analytic expression for each of them. And we are summing until n, and we were putting 21 eigenfunctions. Okay. This is just the equation for the solution. Then we mount together the solution by just taking the product. We had the mean flow, which is just the parabolic profile. And then here you have make a GIF. If you want to make an animation of this profile or not, you put false or true. And based on that, it will produce an animation. So let's say I put here true. And I run until line 24. Do you see the animation coming on your computer? You have it? Very good. So this is now, let's say, your collection of data sets. Now from that, we will look at the POD modes. Then it would be nice to have a discussion on the link between the POD modes and that. You see that they are very different. Okay. 20, for this case, you use 20 eigenfunctions, and you see 3 POD modes can do just as well, or very close to that. You have it also here on this side?
There are some libraries that are not installed.
Which one?
SciPy.
SciPy you should install. That's a very important use. If you are in Conda, you just type Conda install SciPy. Here you have it. Now, okay, this is a test case which has an analytical solution, very nice. But what if we have to solve this numerically? Do you know how to solve this numerically?
Differential equation.
Yes, for example, with finite differences. I just want to throw a warning here because we said that our POD modes are orthonormal. Yes, but with respect to the inner product that we have defined. Okay, so let's do this in a discrete way so that we will make sure that the orthonormality holds. Okay, so in a discrete way, our velocity profile is, guess what? A vector. It's a vector which is moving in a, if I use 2000 points, it's a vector moving in a 2000 dimensional space. And with the POD, what we are trying to do, we will look for a subspace. Okay, let's say if I use only 2 POD modes, it would be like a plane. And we will look not at this vector moving around, but at the shadow of this vector on the plane that we have selected. Okay, but first we need to build this vector. Okay, because that vector is what let's say is governed by our discrete equation, which has been obtained by discretizing the problem. So let's try to do this together. I'm going to solve it in one way, which is not the best way of solving it, by the way, but it's probably the best way to show this idea. So we had this, and then remind me where was the W and the PA? You all obtained this, right? Now I'm going to use 2000 points and we will use 300,000 time steps. So we will use an explicit scheme. Okay, so the equation is something like this. Here we have minus PA over W square cosinus of t, and then the only funny part here is the second derivative of it. Okay, so this has to become something of this form. Let's say I put it like that. Okay, so I want to use what is called an explicit scheme. Okay, so given my time step n, I want to say what is going to be the next one. Now, to do that, we will need a way to discretize this guy and a way to discretize this guy. Let's begin with this one. Well, if I use a central different discretization, what will this be? So let's say I have many points here, and at position I want to approximate this operator at this position, okay, using finite differences, and I can use a centered scheme.
I plus 1 minus I minus 1.
Minus 2 and 2.
Yes. So I plus 1 minus 2 ui plus ui minus 1 divided by delta x square, no?
Yeah.
You agree? Good. So this will be our way of representing that. Okay. Now this is a linear operation, right? The derivative. So every linear operator can be written as a matrix. Okay. So you have now to find the linear operator, which I think I call it L, which implements this, respecting the boundary conditions. Okay. So you can see that this will lead to a matrix of the form 1 minus 2, 1, 1 minus 2, 1, which goes down like 3 diagonal. This part is the easy part. Then the trick comes when you go on the first and the last, because that's where you will put the boundary conditions. Okay. So if I have discretized, let's do it for this case. If I take 1, 2, 3, 4, and 5. I'm not going to solve for these points, right? Because those points are the boundary conditions. And in this case, it's a wall, it's no sleep. So I know this will always be 0. All I need to advance are these three guys. Okay. So the operator which I will need should be 3 by 3. So if I have, let me number them 0, 1, 2, 3, 4. I only need to advance 1, 2, 3 because 0 and 4 are fixed by the boundary condition. So I need a linear operator here which advances U1, U2, U3. This one is very easy. I'm just applying that, of course, here divided by delta x squared. This one we have to be careful because you have to consider that when we are here, we are going to hit this boundary. Okay.
-1.
Let's see. If I ask you, for example, dy u at the position 1, just use this formula. It will be u2 minus u1 plus u0. But this one is 0, right? Because it's your boundary condition. So here we will have just there was a 2 here, there was 2 here, sorry. So you will have a -2 here, a 1 here, and then nothing else, right? Similarly, if I go now to the last, here we will have u4 minus 2u3 plus u2 divided delta x squared. But this one is 0. So we'll have -2, 1, 0. Okay. So the way I suggest you check that, you write the general form, then for these ones, you have to make your consideration depending if you have a Dirichlet, Neumann, etc. Okay. For the time being, this is going to be our matrix, and in this case, it's going to be, if I have a dimension of 2000, it's going to be 2000 by 2000. Okay. Is this clear? So I will approximate this as L times U at time step n. Okay. This one, well, there is nothing to discretize here. It's a source, it's constant everywhere. It's just going to change as a function of time. So let me call this source as a function of time. And usually, once you're in this situation, you are done with the time domain. Now, when it comes to with space domain, sorry, when it comes to time domain, you can pick now your discretization in time. It can be Euler, Runge-Kutta, it can be implicit, it can be many things, right? But if I stop here, I have written now a system of ODEs. You agree? It's a system of ODE which is going to advance in time our 2000 points or something like that. So for this exercise, I will pick the simplest possible approach, which is, say, the Euler integration. So now this will become un plus 1 minus un divided by delta t. This is, we call it Sn, and this is our plus L times un. So from here, our solver will be this, right? So you can just write a for loop. This one you have, this one you can compute, it's just cosinus of time at the time which you are. You write a for loop starting from an initial condition, and you advance in time your 2000 dimensional system. Is this clear? Now, what is one big property of this matrix L? Because of what you have seen, it's very sparse, right? It's full of zeros. So it is very convenient not to save this as a full matrix, but as a sparse matrix. You know what that means? It means that in the storage of the matrix, you will not store the whole matrix, but you will only store the coordinates of the points that are different than 0 and the associated value. In Python, you can do this in just one line of code. You just declare your matrix as a sparse. So this is happening here. So there is a function which I put in the auxiliary function called get Laplacian, which will build that matrix. And notice that I'm giving as a number of points ny minus 2 because I'm excluding the two boundaries. Okay. If you run, let's run until L. Follow me until L. Yeah, so from here, so from 98 until 124. If you are using Spider, you can have a look then at the matrix L in your space. You see it has been declared as a sparse object. You can spy it. You see, it's compressed. There was a way to show it, but I don't remember it. There's a spy thing to check where it's different from zero, okay? If you go into the function is, you know, in Python, you can highlight the function and then right click and go to definition, and you find the function what it's doing. So it's just creating a string of ones and -2, and then filling it as a three diagonal matrix. And then at the end, this declaration is to convert it into sparse. Okay. Is everything clear? Now, there's one thing that I didn't mention is that this, and that's why it is not a good approach to solve this problem, is that this is not, you're not free to choose the delta t here, right? There are some stability criteria that you have to follow to make this work, okay? And the stability criteria is that the CFL has to be smaller than 0.5 for this problem, no? So here you have, I forgot something. Here there was the 1 over delta x squared, right? I forgot the delta x squared to this. This will add the 1 over delta x squared. So then here you have this parameter lambda appearing, which is the delta t over the delta x squared. Okay, so because we need to have that number, this lambda here, be smaller than 0.5. Once you have picked your delta x, your delta t is going to be defined. It's going to be very narrow. So in the code, you have that I don't want to save all this data set. They are too time consuming. So I'm saving here every n save iteration, and n save is 50. Okay, so every 50 iteration, we will actually store our result. This will compute, but store only every 50.
Why 0.5?
Because if you do a von Neumann stability analysis for this one, you end up that above 0.5, this will explode. Okay, that depends on every scheme. Every scheme has its own limit of stability. Okay, but I believe you see this in numerical.
For PDEs, but
Okay, you could find for every scheme.
we normally give them the conditions because it's another element of you know, doing the Fourier and looking at
Yes, the Neumann analysis. Yeah, there is a stability analysis you can do, and you will derive this condition. That depends on this combination that you have picked. You can also pick combinations that are never stable, for which they will never work. Okay. So if you look at, so let's see what is this code now doing. You have a for loop. So this one is computing the source. So this term, remember that the source has to be a vector, because you're summing these two other vectors. So it has to be the same size, but it's uniform everywhere. So we are multiplying it by a vector of ones. So it's acting everywhere. Then vec n plus 1 is essentially doing this. So CFL is this lambda, it's a scalar, I can write it anywhere. Then you have L dotted with the vector, so the current solution, plus you have this part here, okay, plus vec, which is this part here. And this is just looping in a for loop. Is this clear? So we are advancing a dynamic system of dimension 2000. My computer can still handle this relatively easy. I hope yours also. So I encourage you to run until 154, okay? We're going to run for 6,000 steps. And now I would like to be sure that there are no mistakes on this one. This one is correct, because now you have to do the Galerkin projection. So u plus 1 is equal to source, let's call it source, times delta t plus vec, and then you have L dot U times CFL. So this one is correct. Write it somewhere because now you will need it. Okay. Now, after you've done this, we do the POD. The POD will give us the phi's. Okay. I believe you don't have the code there, but you should go line 173. Is it your line complete or you have to fill it? Line 173. So this is where we are going now to compute the phi, the sigma, and the psi. It's filled. Okay, that's the SVD. Okay, or the POD if you want. Now, what is the most important thing that you will look at now? First, I will look at the sigma. And you look at the sigma, plot them. Takes a bit of time to compute. Huh? I picked NP dot, the one from NumPy is the slowest.
Call PCA.
Sorry?
You can call PCA.
Of course. Please feel free to remove this and put any other way for computing that. Okay. Like 5. You have? Oh, mine just ran. I get something like that. You have the same?
We didn't get the results because I guess we have to upload the libraries to Google Drive and then to use them on Google Colab.
Using
Yeah.
Cloud.
Okay, we'll try it. At
We
home.
check it at the
Yeah.
break. Okay. Did you manage? You managed? You guys managed? Okay. We will come back to that, but let's say, so trust me that you should get something like that. Trust us, in fact. Okay, so you trust us and you decide how many you want to pick. 3 is enough, right? We pick 3. Agreed. Maybe 2 is enough. You go for 2, you go for 3. Okay. Okay. Good. But now, how do we go for 2 or 3? Let's say, in the interest of time, we will go only for 2. What does it mean to have that that sigma? I mean, to have that decomposition. If you look, I think I was putting it here in the slides. So you have to imagine now that every UN is going to be a linear combination of those three guys. So I could now take this equation and replace, instead of un and un plus 1, I put that, okay? Where the index is only reflected in this coefficient. If you do it on the whole equation, you obtain something like that. And then, for instance, I multiply this by U1 transpose, sorry, phi1 transpose. So look at that equation and imagine that here, I don't want to write on that, but let's say that I multiply it by phi1 transpose. And now you tell me what is going to come, and then we go to have a coffee.
Just get A1.
Okay, let's go step by step. So first, let's go on the left. First term that you will get is
A1 n plus 1.
A1 n plus 1. Then the rest.
I see.
These are all dead, right? So equal.
The CL A1.
We go first for this one, maybe.
A1N.
A1n, yes. Plus lambda c. Then what else? Before L, we remember we multiply by phi1 transpose. Huh? So I will have phi1 transpose L phi1. What is the dimension of this? So dimension of phi1 is ns, let's say. This one is ns. In fact, is -2 because you remove the boundary condition, but let's trace over of that. Okay, and this one is it's been transposed, so it's 1 over ns. This is 1 ns times 1. So the outcome of that is what? It's one number. It's one number. It might be expensive to compute, but it's just one number, and we do it only once. Okay, then times A1. Then to the end. The other term will be what? Guess what? It's going to be the same, right? These terms are obviously not 0, but they are numbers which we can pre-compute and store. Okay, blah blah. And the last is going to be something like phi1 transpose times our source. You agree? You do this 3 times, and you will obtain a system which you will fill after the break. Okay, so the coefficients that you have here are all of this power. So I believe that in the code, and this one I did left it open, you find something like that, and you have to fill it. Okay, after the break.
So we'll break now if you.
Yeah. So in the interest of time, I'm showing you the results. I mean, just copy this, you just copy paste the first line and then you modify the others. Okay, so C1, 2, for example, is the dot of phi1 ls phi2. You notice that I'm using this NP lin alg multi-dot. This is a very nice tool to compute product of matrices because it will automatically look for the most convenient order to do the multiplication. Okay. Good. So this is preparing the coefficients C1, C2, C3, which are the ones that we have derived here.
You have them, it seems.
No, this one you don't have.
This one.
This one you don't have. If you go below with the coefficients, I think you don't have.
No, they're yeah, well, some of them do have them. I don't know, it's the outdated version.
Which file have you opened? Ah, because I gave you both Galerkin and Galerkin to give.
Ah, okay.
So you're not in to give, you are in Galerkin.
You're cheating.
So it's okay. In fact, I didn't notice that I already gave you. So you have 2 files with the same name, but one has also to give. The one to give is the incomplete. Usually I prepare the file, then I delete some lines, I save them as to give, and I give. But so well, it's a matter of copy paste. You understand what are these lines doing, right? These are computing the 9 coefficients which we have seen here. Okay. If you want to try with only 2 modes, just remove the coefficients appropriately. And then you can go to the last part of the exercise, which is nothing more than running this system, which we have written here together, for the 3 A's. Okay. So you have again the usual loop, where you have the usual store every 50. Okay. And that produces now the evolution of all the coefficients. And when you have this, you can remount back the solution using the phi's that you had before. Can you run until this so line 274? So this block here. It should hopefully go much faster than before, because now you're advancing 3 numbers and not 2000. Okay. No, please.
Down.
SFL. Which line?
Yeah, here.
Ah, good. Thank you. No, very good one. Is this lambda? I put it in the slide, but I didn't say it. Yes. So it's computed before. In fact, this one is what you usually fix. For example, I know that my code is stable with the CFL 05. You put it at 05, and then from there you compute the delta t. Usually you have the delta x. You know what is your lead CFL limit. So from there you compute the delta t. Okay. More questions?
So U underscore N underscore red are the solution for everything at the end of the end.
Sorry?
With in Python code, when we have reconstructed at line 274.
Here you have the
So,
reconstruction.
so we're constructing from the coefficients.
Yes. Here now we are solved for the coefficients, and we will reconstruct the full solution from there. Because we remember we said from the beginning, when we put the things here, what we were putting here, we were saying that UN, so U at time step n is going to be A1 n times phi1 plus A2 n phi2 plus A3 n phi3. Now we have solved for all the A's, the fees we had, so we can reconstruct. So you should experience the fact that it goes much faster. And now if you look at the reconstructed versus the original one, I put the result in the slides. You will see that they look really similar, in fact. Yeah. So this is an animation where we have in blue the result with 2001 points, and in red the reconstructed. So it was a good idea to be, so 2 will have led slightly more error. Like that, we still have some error, but come on, it's not too bad if we know that we moved from 2000 to 3. Now, there is one important critique that you should ask here and say, wait, okay, we speed up the computation, but we had to do the computation to get the files, right? So here, I think the applicability of these ideas branches into 2 possible directions. Either you have the files from somewhere else. Maybe you have data from somewhere else and you have computed them from somewhere else. And so it's just about using them, and you are going to save the computational effort to solve the whole problem. Or for example, if you're doing some regression, you want to find some missing terms in your PDEs, it might be good to project your PDEs so that then you work on the reduced space and the regression is easier. Okay. So this is, if you want, is the world where the files are coming from somewhere else. And there's another world where you don't have these files. You have to have also a solver, like what we just wrote. And this is a very active area of research. The idea that you can have a solver that can advance your simulation. Time to time, it might stop, see what has accumulated, compute the POD, and maybe alternate between full power simulation and some and reduced one, full and reduced, full and reduced. There, the big topic becomes, yeah, but how long can you go full, and how often can you then switch to the reduced, and how expensive is computationally recomputing all the time the POD versus just go with the full. So there are many practical considerations that goes into this picture. And one interesting area of research is also the idea of doing adaptive files. So every time I compute a new solution, I update my previous implementation of the VOD. You try to always improve it on the fly. So you always update. This is also a cost. Okay, but just to give you a flavor of what are the possible applications of this. Okay. So there was another comment that I wanted to address here, which was the comparison between, I found this, the first time I saw this in this exercise, I was a bit surprised. Because looking at the spatial structures of the POD and looking at the spatial structures that you will get from the eigenfunction expansion, you will see that they are very, very different. If I plot here the sigmas, so the amplitude of the POD modes and the amplitude of the eigenfunction expansions, which we have accumulated, which we wrote before analytically, you see that the POD modes go faster than the normal eigenfunction expansion. Are you shocked? Me, I was a bit.
The eigen.
This will be
The correlation or for the data?
no. These are the one analytically coming from the So if you solve the PDE, how will you solve this PDE? Normally, you will do the following. You will use separation of variables, right? You write the separation of variables. Then you obtain two ODEs. One is a boundary value problem. The other is an ODE. The boundary value problem will have its own eigenfunction, which in this case is just the Laplacian, so it will bring you cosines. Okay. Then you also project in a way into your an ODE, and then you integrate it. Okay, if you want, I can give you the full derivation of that. But the philosophy is very similar. What changes is the basis. Somehow, the choice, the POD choice is convergence-wise, in terms of approximation, significantly better. Okay. And what is nice, and this I leave it to you as an exercise, is to check the difference between these two. So, for instance, is this one orthonormal with respect to our inner product? I don't say you anything. I would like you to check that. This, you know, it's orthonormal to your provided inner product. That came as a solution, but this one, you check. Okay. So this basis was being somehow tailored by the POD, such that you get the best energy out of that. It is clear. If this is clear, then I will close this part on the POD and go towards the following part. No, maybe I will show you something else. This optimality, you remember yesterday, this is in exercise 3.1 to give. Yesterday we did the we did the DFT of the cylinder. You remember the cylinder flow? Mm-hmm. And then we built an approximation with something like 50 Fourier modes, you remember? And we looked at what was the approximation coming from, the error coming from there. So if you open this file, I think this file, even if it's to give, it should be complete. What we're going to do is we launch the POD for the cylinder test case, which you've seen before. And we look at the spatial structure and the temporal structures. I don't know if you managed to run this file, but here I'm plotting already all the results. So this is the behavior of the amplitude, of the sigmas. Again, and you should not be too much surprised by that, the POD is leading to a convergence, which is impressive, right? I mean, only 3 modes, and we are already at almost 1%, let's say, of the first mode. What else do we see? We see that these two also leading modes, together with that one, have the same amplitude. Exactly the same amplitude. Why is that? Now, the POD is approximating your dynamics as a combination of things that have to pulse in time. And this data set has some traveling waves, some traveling shedding. How can you approximate something that is traveling with something that is just pulsating? You need to sum 2 of them with in quadrature, okay, with a phase lag, such that, like the ola in the stadium, right? One goes down, the other goes up, so that with the right phase delay, you produce the traveling wave. So POD is not really efficient in representing traveling patterns. It will use always 2 modes with the same amplitudes and very similar temporal and spatial structure, just shifted by the right amount. So this is typical result that you see here. What else do we see? You remember what was happening in this data set? We had that the flow was going from fast and then to low. The first POD mode, if you look at the temporal evolution, look what it's doing. It's capturing the large scale dynamic of this data set, which in fact was going from high velocity towards low velocity. The spatial structure associated to that is some sort of mean flow, which is evolving from large to small. So it's a sort of very large scale. But this is the Fourier transform of the temporal evolution. So to look at what is the frequency content which is in these modes. You can see that mostly low frequency, because you can see it here. But there is also some high frequency there. I mean, the spectra is very broad. If you look at the second mode, here's what we see. So these 2 guys will come in pairs because they have to describe the traveling wave which is in the data. This traveling wave has the shape of vortices. This is the vortex shedding. A combination of these 2 will produce the vortex shedding. From here, we can guess more or less what is the characteristic size of these vortices. We can also look at their temporal evolution. This is their temporal evolution. You can already see that something has changed at almost 2.5 seconds. You see the shedding was a high velocity and then reduced. We see all this information beautifully, very nicely condensed in this plot. And if I take the Fourier transform of that, I see 2 peaks, okay? We are not surprised by that. We know that there is a certain frequency here and a certain different frequency here because the mean flow has changed, okay? And if you look at the other modes, it will have the same, but just shifted, okay? It will be not possible to recognize them. This is the beauty and the weakness of the POD now. We only talk about the beautiful side, compression, very good. But if I ask you to tell me whether this structure is mostly linked to this frequency or this frequency, you don't know, okay? Because of the optimality, the POD just tried to put everything it can put into few modes. Okay, that is the idea of it's designed for that. It's designed to give you as much information as possible in fewer modes. Okay.
Yeah, do you mind just resharing screens because we have this problem?
Oh, sorry. Okay, check it. Oh no. Stop share.
Yeah, it's okay.
Ah, it was okay. Okay. Now, yesterday we built an approximation with the Fourier modes, and we picked 50 leading DFT modes. We got an error of 22.8% in our approximation. Now, if we take only 3 POD modes, you get an error of 15%. Okay, so in terms of convergence, that's really the best that you can have. There is no other linear decomposition that can achieve the same result for an equal number of modes. Okay, you cannot beat it. At the best, you can be as good as that, but not better than that. Okay. Why it is particularly interesting to have just these three modes? Because then you have three psis, three temporal evolutions, and you can plot them one versus the other, and you reconstruct the orbit of this reduced dynamical system that has only dimensionality 3. This will be what will happen if I solve with the Galerkin projection only for the three modes. I will have a dynamical system of dimensionality 3. And if you plot it, you obtain these results, which is quite beautiful. When you are in a steady state condition, so one of the steady state, the way the POD pictures that is just like a pendulum. Okay, you have like a circular orbit. This is not animated, but you can. I invite you, if you want to do this plotting exercise, to animate that, to plot the evolution of the A's in this world. What you will see is that they are around an orbit when the flow is at a first steady state flow, and then as you change the free stream velocity, they will evolve around the manifold, which is like a paraboloid, and they will land into another circle. 4,000 dimensions, 3 dimensions. Okay. Now this exercise is, I usually give it because it's the most remarkable in terms of compression. I don't want you to believe that every flow field can be mapped back to a pendulum. Okay, but this one can, and this is a fairly noisy real data of a flow of fairly high Reynolds numbers. So it was not obvious at all that you could map all these dynamics back to a pendulum. And you can always decode this, right? I mean, you can establish a mapping from any of these points to any of these points. So if I can do regression here, maybe I want to fit a Gaussian process or a recurrent neural network to predict the dynamic of that. And I can play all my life in this world and then map back to this world. Okay, of course, provided that the modes follows you, right? If you start modifying the dynamics, that's also not a very active area of research. For instance, for control purposes, if I want to inject here something to try to reduce this wake or stuff like that, and I want to know how the system will respond, I might want to do some quick simulation. I cannot afford to solve Navier-Stokes to the whole problem. I can try maybe to solve on the reduced one and then reconstruct. But there's always the question, yes, but once you start injecting things, the modes might have been different than the ones that you have derived before. So then the question of adaptivity of the modes comes. You see, these are all, we are really talking about the frontier of the research. Okay, these are all active areas of research. Okay, do you have questions on this? Normally, if you run this script, you would produce all these figures, all these plots, all these things. Now, I will jump to another topic. Yes, please.
There's a field called solving PDEs using spectral methods. Like there's a famous library on Python called Daedalus. I don't know if you heard of it, but it uses, let's say, Fourier transform Chebyshev to simulate where does what you did in the previous exercise stands by.
This is a beautiful question. It's a beautiful question. There are 3 words that talk to each other at the intersection of this exercise. They all have in common the Galerkin projection, but they are completely 3 different fields. One will be POD-based Galerkin projection. The other will be what you've mentioned, spectral methods, using Chebyshev or the like. And the other one is going to be finite element methods. They are all sharing the same ideas. They are all sharing the idea that I will approximate my solution as a linear combination of some bases. All of them. The difference is that in finite element methods, usually these bases are localized bases. For example, you have your mesh, you discretize your mesh like that, and you place your bases somehow near these meshes. Sometimes they are not orthogonal with respect to the usual inner product. So you might want to add a weight function in the inner product, that would be your test function, to make them orthogonal. But finite elements is the world in which your files are local and build around your elements. It can be first order elements, can be second order elements, higher order elements, etc., etc. Spectral methods are those in which the bases are usually global. Typical example could be Fourier, in the case in which you want to use Fourier-based solvers. You can have Chebyshev, you can have Legendre, you can have many other polynomials. How do you pick? Which one will you take? It depends on the boundary conditions. Because here you build your operator in such a way that was respecting the boundary condition. But if you use your bases in a way that you construct them such that they already respect the boundary condition, then you don't have to care about boundary condition. Typical example, you have a PDE and you want to solve it with periodic boundary conditions. You put Fourier, easy, we don't care about boundary condition. Or maybe you have some Dirichlet conditions, then you will pick some Chebyshev polynomials. You see, you choose your basis, but somehow in both cases, you are constructing the base. This usually tends to be more general purpose, tends to be less accurate than that. Okay, if you have a periodic problem, go all your life with spectral methods, for example. Okay, or if you have a boundary condition that lets you put the basis easily, this would be very nice. They starts to become difficult, hard when you have strange geometries. For example, imagine solid mechanics. I want to simulate, I don't know, the mechanical resistance of this chair. Okay, in this case, the volume that I want to simulate is the mechanical part of this chair. It will be very difficult to find the basis nicely positioned such that they respect all the conditions, so on and so forth. With finite elements, it's easy. You break it into your sub-elements and you build your meshes that exist all in those sub-elements, and that they are orthogonal thanks to their locality, in the sense that if you have a basis here, does not talk to a basis here, so of course it's orthogonal to that. Okay. And then you have the BOD, where this basis comes from somewhere else, comes from data. Okay. That is also a world where you usually don't care about boundary condition. We didn't have to care about boundary condition here, somehow because L was already respecting them, and also because the files were respecting them. Okay, they come from data that had those boundary conditions, and the PUD will respect them. Okay. But they are three words. You can find many books on each of them, but they are all connected on the Galerkin idea. Okay, is this clear? More questions? So normally, now I wanted to, the course normally evolves in this way. We saw that the BOD is not able to distinguish frequencies very well because it's too much focused on optimality. There exists another side of the world where people only focus on frequencies and not just the energy. Okay, and the quintessential decomposition that does that is the dynamic mode decomposition. The lecture that comes after this one was entirely dedicated to the dynamic mode decomposition, but since we are running out of time, I will skip it. Okay, you have all the codes to do that. You have all the slides where you see the derivation. Very briefly, very briefly, what the DMD is going to do, they will try to fit a linear dynamical system on your data. Why? Because a linear dynamical system, its evolution depends on the eigenvalues of the propagator. So from there, you can look for frequencies very precisely, much more precisely than Fourier. It's an exercise that I didn't ask you to do yesterday, but it would be nice to do. If you take the example which we solved yesterday was from -pi to pi, you remember, And because it was from minus pi to pi, the Fourier was spot on the right frequency. You noticed? So you had the problem like that. And if you take the FFT perfectly on K1, -1 and K1, you've noticed that. So with Fourier of that, we were getting exactly the right frequency. But what happens if instead of showing you the domain from minus pi to pi, I show you, say, I don't know, from minus 2/3 pi and 2/3 pi, or let's exaggerate, pi half and minus pi half. And you do the FFT of that. What do you expect is going to happen? Do you still see this very clear peaks? It squiggles a lot. You know why? Huh?
It's not localized, it's for.
It's not that the reason. The reason has to do with what you also said last time about the choice of the first frequency. In the Fourier, all the bases that we are putting there are periodic. So a linear combination of periodic stuff has to be periodic. If you have chopped it in this way and your signal now becomes, say, something like that, this is not periodic, because if I mirror that, the next step will be this. And the next step will be this. You see? In that exercise, I picked precisely minus pi to pi to make you see this and be happy. Okay? But the reality is that this, you almost never see this. So because your boundaries are not exact multiples of your fundamental tone, the Fourier will picture your signal in this way. And so here you have a big jump, right? And to represent such a big jump, Fourier will start needing many more frequencies here. As you said, it will wiggle, okay? You will have more. This is called spectral leakage, okay? It's coming because your data is not exactly periodic, but you assume it to be periodic. Bad stuff. So in signal processing, we have lectures on how to try to avoid that or to limit that. One way is to window it or to try to make extensions in such a way that you mimic it to be as periodic as you can. There are tricks to try to combat a bit that, but it's a limit that will always be there. One solution is what you were saying yesterday, to try to find different bases, okay? To try to make it not, it will always have to be periodic, but it depends on how ugly is that jump, to try to limit a bit this jump, you see? That's why I told you that is not a bad idea. You can have cases where you might want to change a bit the fundamental tone. Okay, is this clear? Now in the DMD, you release completely the condition of having that multiple of a fundamental tone. But if I have to summarize the entire DMD lecture in just one slide, I will pick one slide that summarizes it. Is a slide that compares DMD with the DFT. Here you have all the derivation, also a bit of esoteric links to Koopman analysis. I skip all of that and then jump to this result. So on the left-hand side, you have the DFT case. All the modes stay on the circle. This decomposition is always stable. I mean, Fourier will never explode in your hands, and this is perfectly fine. This is orthogonal in space, okay? However, you have that the frequencies have been constrained. This is not a data-driven decomposition. You picked the bases. You might find some clever choices to limit the spectral leakages, but at the end of the day, you have picked the bases, okay? You can have spectral problem, is what I just discussed. But as I said, it's always stable. And it gives you an excellent basis for a periodic, problem. The DMD, as I said, will try to fit the linear dynamical system into your problem. So you will now have eigenvalues of this dynamical system that might be on the circle. In this case, they will oscillate forever. Or they might be inside the circle. In this case, they will die. Or they can be outside the circle. In this case, they will explode. okay? Almost never orthogonal modes. So you saw the stuff that I was telling you about the encoding and so on. Very difficult to do it with the DMD. You can do it, but it's usually not easy to handle. On the other hand, you have no windowing effect. There is no constraint whatsoever on what should be the frequency that that these modes can have. Okay, and as I said, it's potentially diverging. It's an argument very powerful, but also very, very fragile. My experience, half of the time, it didn't work.
So we can do Galerkin projection.
No. Good point. We cannot do Galerkin projection on that. You will need to reorthogonalize the basis a bit. You will have to do some extra work to do that. It's not as simple and straightforward as it was for the POD. So if your only focus is Galerkin projection, I think POD is the tool. But if you're looking for harmonic patterns and your POD is giving you modes that are mixing frequencies here and there, then you might start considering the DMD or what I'm going to show you after that. Okay? A very high level summary of the whole DMD. Do you have questions on this? Now I show you just the result for this part. This is the esoteric part that you can jump, and this is how you do it with Modulo. So you have you call your Modulo object, you have your data, and then you have one line: compute DMD PEEP. Why it's called PEEP? Because in fact the first DMD algorithm came much before the DMD and came from climatology, and it was called PEEP. It stands for, you had PEEP and POPs. One was principal oscillatory patterns, and PEEP I don't remember, but these ideas were there in the 90s already, okay? Then it has been, let's say, reshuffled and repurposed, and now you see it more as DMD. Many ideas were already there. So all it wants, once you have given the data, is the sampling frequency. In this case was 3 kilohertz, and the output will be the spatial structures of the DMD modes, the lambdas, the ones that the eigenvalues of our best linear system in the data, the frequencies associated to that, and the amplitudes. Now, these are to be interpreted as initial amplitude, because if your data is exploding, what is the amplitude? Is this just the amplitude when you start? If it's oscillating forever, that is the amplitude, okay. But if it's vanishing or exploding, then the notion of amplitude doesn't really make sense. That's why I call it H zeros, because it's somehow the amplitudes at the first snapshot, okay. The rest is an exercise in plotting. So here I was plotting, for example, the lambdas in the complex plane, so the imaginary part and the real part, together with the unitary circle to see where we are on the circle. And here I was plotting the frequencies versus the absolute value of the lambda. These are the results for the cylinder test case. You see that most of the modes are inside the circle, so they will die, in fact. There are only 2 guys which are not dying, which are really close to the circle. Unfortunately, because of numerical errors, they are never exactly in the circle. Maybe they have a modulus of 0.9999. And you may say, oh, that's 1. Yes, but when you have 20,000 snapshots, 0.99999 powered 20,000 times is still 0. Okay. So also another thing that is often, let's say, not said about the DMD is that you might not expect the convergence to actually work. Okay. You might not expect the DMD to be able to reconstruct your data set. You might expect the DMD to find the leading frequencies, okay, which it did. If I plot these eigenvalues with respect to the frequencies, is spot on 450 hertz with no spectral ligand or nothing. This was really the shedding frequency. This was just at the first transient, which was very good, and it's giving me directly the modes associated to that. So it's amazing to localize frequencies, but don't expect it to give you an error and to converge to your data set. Okay. Here first, because here everybody dies in quite quickly. This guy take a bit of time, but they will also die, and this one will take a lot of time to die, but they will also die. And if they are slightly outside the circle, there will be an explosion. This thing will go to infinity. Okay. Also very interesting if you want to do linear stability analysis based on data, okay, to see what is outside the circle, stable, unstable, etc., etc. Okay. That is my 10 minutes lecture on the DMD. Do you have questions on that? If not, then I think, I don't know if we want to take another break, I think time-wise. Okay, so to recap, POD, energy, DMD, frequency, both have problems. The next lecture is about the way to find something in between. Okay? Well, break then. Okay, so welcome to the last push, and now we are going to be really at the research topics. Okay.
Again, the screen.
Sorry. Thank you. So, as I was a bit anticipating in the previous lecture, the POD and the MPOD, sorry, the POD and the DMD, they both have some limits. I will briefly recall them, and then I will show you 3 hybrid ways of trying to take the best of the two words. And then there is an exercise which is going to be an assignment. You play with that at your own time. So, as I said, you have these 2 different words: energy, and nothing else. Meaning that all the modes are by construction optimal. They give you the least error that you can have. And the decomposition is also very robust. But you can have possible spectral mixing, which is what we have seen before in the case where a mode was taking frequencies from two different times in the flow. On this case, you can have a wonderful spectral separation, look for the exact frequencies, but you have problems of convergence. You have also problem of time localization. This is obviously related related to the fact that if you want to be very precise in the frequency domain, you cannot be very precise in the time domain, right? You know this very well. It's also the complex balance that you have in wavelets. When you want to find a frequency with a certain precision, you cannot localize it in time with an equal precision. The notion of frequency is implying something that lasts forever. Okay, if I ask you, I have a wave of 1 Hertz, and I ask you, okay, when did this occur? If it's 1 Hertz, it means that you need to give me at least 1 second for me to see a period. So you cannot ask me to be precise and tell you, oh, 1 Hertz occurred at 0.5 seconds. You cannot, right? So in the moment in which you want to localize a certain frequency in time, you have to drop the idea of wanting to be perfectly spectrally pure. Okay, this is something that the POD can handle in theory, except that it's working so much into the energy that that is potentially mixing the things, which is what it did in the case of the cylinder. So there are some hybrid ways. We will review 2 of them. One is the spectral POD by Siebert. These 2 we will not review. And there's also another one I forgot to mention to put here, which is another spectral POD. That is the one by Tone et al., but that is more on the frequency-based approach. And then we will review another approach, which is the multi-scale POD, which in theory was designed to try to take the best of the 2 worlds. Now, to show you that, I wanted to provide you another test case, which is in stationary conditions. So in principle, it should be really the best you can have for frequency-based or for POD decompositions, where you also see the spectral mixing of the POD in action. Okay, so this is the case where you have the impinging jet. We saw this data set, I think, in the first slides. Time resolved PAV, and I'm going to skip all the details of the measurements. But what I'm going to say is that if you look at this data set and you look at the frequency content of this data set, here I'm placing 6 probes, and in these 6 probes, I'm looking at the spectra in dimensionless form, so in the forms of a Strual number. What you see is that, so the nozzle is somewhere here on the top, okay? So in P1, you have a strong leading frequency of 0.3. This is the classic Kelvin-Helmholtz instability. Then as the jet goes towards the wall, the velocity decreases, and as the velocity decreases, the frequency decreases. So you see that the spectrum moves towards lower and lower frequencies. When you are then on the wall, here in the so-called wall jet, where the velocity is very low, we have very large scale structures. So the frequency content is really going towards very, very low small numbers. If you do the POD of that, and this is in the exercise 5, you will observe this. I'm not showing you, to be fair, I'm not showing you the leading modes, but I'm showing you some modes where you have a tremendous frequency mixing. So for example, if you look at this structure, this is a structure which is supposed to have a frequency somewhere around 0.15, but it also has much more, also very low frequency content. And one could expect, if you have some experience about jet flows, that this low frequency is due to things that are happening here. And in fact, this POD mode has also some stuff happening here. It's again mixing the things. This one has mostly low frequency, so you see it's mostly in the wall jet where we observe this low frequency. But there is also something else here that is coming from this portion of the flow. And this one is really the most problematic one. Here you have some structures in the wall, which are most probably linked to this low frequency. This I know because I know the flow, but otherwise it would be difficult to say. And you have here a big guy at 0.3, which is coming from the Kelvin-Helmholtz structures that were near the jet. But again, the POD put all of that together. What the MPOD will do, spoiler, it will give you this. It will create blocks and say, okay, if you ask me to focus on this region of the frequencies, then there is almost nothing on the wall, and most of the things are happening in the jet. And if you want me to focus mostly on this very low content, there's almost nothing in the jet. And if you want me to be in a much larger frequency range, then it's only here that you have this higher frequency range and nowhere else. Okay, so we have the ability of both looking at frequency domain, but at the same time, as I will show you, also in the time domain and in the space domain through the spatial structures. Okay, if you look at the convergence of this test case, for this one with some push, we managed to make the DMD converge. You see, this is the number of modes which you put in the decomposition. This is the convergence of the DMD. This is the convergence of the POD, which, as I said, is unbeatable. You cannot do better than that. And if the DFT is somewhere here, with the MPOD, you can try to be as close as possible to the POD. The price to pay is that we will never be spot on the POD, okay? This is impossible. But if we have to lose convergence, we don't want to be here, not here, okay? So try to lose it as least as possible. But before we go to the MPOD, I wanted to give you a flavor of how people have come with different ideas to try to limit the problem of the spectral mixing of the POD. The first idea which I will present is the spectral POD by Toll et al. You have the paper mentioned in the slides. And the idea is the following. You remember the DFT? You remember what we were doing when we did the DFT? You have a data set, then we encoded it using the Fourier matrix, and we had the matrix that had the spatial distribution of frequencies, and then we further normalize to get this. Remember, this was the DFT. Now, what do we do with the SPOD from this group? We'll do the following. You take the data, you break it into portions, blocks. They can also be overlapping if you want. Now, for each of these blocks separate, you will do the DFT. Okay, so on each of these, you will project, you will do the standard DFT that we mentioned, and you will obtain blocks of this form. So you will have a number of spatial points and frequencies without doing the additional normalization to have sigma phi. Okay, but this is still the part that contains sigma phi sigma for the Fourier. So, okay, we have NB DFT. What do we do with this? You store them into a sort of a tensor, where you have the frequencies, the data, and here the number of blocks. And then you pick one specific frequency, one at a time. And you build a new data matrix, which is coming from all the DFTs in the various blocks, keeping always the same frequency. Okay. And what do you do on this? You do the POD. Okay, so I repeat, you take many blocks, which can be overlapping. You do the DFT on each of them. So I have NB DFTs. Then I put them one next to the other, and I construct a database, a data set, all at the same frequency. Okay, and at the same frequency, I will do the POD. So if I have NF frequencies, I will have NF PODs, one per each frequency. Okay, accounting for the fact that the data has been changing. Yes.
For each frequency, I get a column and I plug it for all the partitions. So I stack them in one matrix.
Exactly. So I try to reproduce this visually. Let's do it again. So you have the different blocks. Let's say 10 blocks. My data set in 10 blocks. I compute the DFT. Remember that the number of frequencies that you can have here, if you use a square Fourier matrix, is the same as the number of time steps that you have here. So let's say I have 5 or 10 blocks of different FFTs, each having 1/5, depends if you had overlapping or not. You can also have overlapping. Then you pick, for each of them, you pick the same frequency, okay? And you build a new snapshot matrix, which will have all the NS, and here we'll have N blocks for each frequency. So if you have, let's say, you have created blocks of 100 each, you will have 100 different PODs, one coming from each frequency. Okay, is this clear? So the way you have to picture that, if the POD normally is a matrix factorization like that, this SPOD will become something like that. So I will have many PODs, many sigmas, many sides, each at every different frequency. So you understand that for convergence purposes, this is really bad, because we started with a simple matrix, we are ending up with a giant tensor here. But the idea here is not to approximate your data set. Here is to really hunt for frequencies, for coherent patterns at certain frequencies. Okay. Once you have done all of that, what you usually do, this block, you trash it. Okay, because this rarely people will look at that because you are assuming that your data set is stationary. Okay, if the data set is not stationary, it does not make any sense to put together block 1 with block 200 if it's too far, if something happened in between. If your data is stationary, then you can put all of them together. If you are familiar in signal processing, there is a technique to compute power spectral densities that is called P-Welch, which is essentially doing the same thing. Yeah, partitioning into blocks, take spectra, then take averages. Here is partitioning into blocks, take DFTs of each, takes POD of each, and then put the whole thing together. So as I said, you will usually throw away those ones, and all the sigmas that were all diagonal matrices, in Modulo, we store them into a matrix which is no longer diagonal. In every row, we put the sigmas of each frequency. Okay, but still we will now have a lot of modes. Okay, a lot of modes for every frequency. So by definition, if we now look for so the first mode of each of these guys will be the leading structure at each frequency. Okay, and if I look at the first row of that, so I will look at the leading sigmas for each frequency. Okay, if you have 100 frequencies, you have 100 vectors of sigmas. For each of them, I take only the first, the leading frequency, and that will give me what I will call the SPOD spectrum. Okay, is this clear? Now, if you run it on Python, that was an exercise, you will see it happening. Here I run the SPOD for this specific test case. Well, this is the SPOD spectra defined, as I said, and you indeed see that there are some spikes here. If I look at the leading structure associated to those spikes, I'm doing quite a good job at finding where that frequency was located in space. Okay, so this averaging is a very good idea. Okay, it's very robust in cleaning all the spectra. For you to have a comparison, if I do the DFT, you will say, why don't you just do the DFT? Yes, here is the result. This would be just take the data, do the DFT. The spectra will tend to be much more noisy. Indeed, the right modes are still going to have the right frequency, but yeah, this is much more noisy and much more difficult to hear. Okay. SPOD, clear. Now, this, of course, as I said, again, works only if you have stationary data. Otherwise, it does not make any sense to put in the same pool the different blocks. There's been another idea for spectral POD by Sieber et al., which was also called SPOD. And the idea is different now. It's also valid for stationary flows. And it comes from a beautiful property of stationary processes. If you have some familiarity with random processes, Gaussian processes, when you have a stationary process, the covariance matrix, the correlation, the D transpose D, has some very specific structure. Okay. When we did the POD, we computed the temporal structure as eigenvectors of this matrix, which was the temporal structure. Okay. Now, it turns out that stationary processes will have a special structure for this matrix. Okay. Do you want to try to guess how this matrix should be? You have questions, please don't hesitate. So do you know how this matrix should look like if you have a stationary process? You know? You want to ask me something or?
Yes,
Yeah, tell me.
What does it mean, like the stationary?
Excellent, I'm coming. So what is a stationary data set? Very good. Stationary data set is a data set that you have various kinds of stationarities, okay? So let's say I have a time series like that. Strictly speaking, stationary process is a process in which its statistics are invariant with respect to time. So I could take this chunk, for example, look at the PDF and the distribution of what I have seen here. I don't know, maybe I get something like that if this is some sort of Gaussian process. But if I take now this other chunk, I have the same distribution. And if I take this chunk here, I have the same distribution also. That is a strictly stationary process. We usually don't aim for that. We are okay with weak stationarity. What is weak stationarity? It means that you can define the degrees of the various degrees of strength for stationarity based on the numbers of moments of the PDF that you want to maintain invariant. Okay, so the weak stationarity means that I have the same mean and the same standard deviation, the first two moments. But I could push and ask also that the kurtosis and other higher order moments are the same. But for us, we are usually okay with saying that the first two moments are the same. So the mean has to be the same and the sigma has to be the same. So if I show you a data set, I mean a realization which is doing like that, this is clearly not stationary, okay? Because the trend, there is a general trend that is growing. The mean here is not the same as the mean here or the mean here, okay? If you have stationarity, what will happen is that the correlation between what happens here and what happens here, say that these 2 points are separated by an interval t, is the same as if I take, say, this one and this one separated by the same time. So to make it clear, this is a random process, okay? If I close my eyes and look at that again, and then I will see a sequence. Then if I close again and look again, I will see another sequence. Every time I sample, I will see a different series. And if I look at one specific one, at this point, I will have a certain distribution. Okay, and each of these I have a distribution. Now, this operator is somehow telling us how two snapshots, two things are related. And if the process is stationary, the only thing that matters is the distance between them. Is this clear?
Having certain distributions over certain intervals, does that mean the function is periodic? 'Cause it's
Not necessarily. Not necessarily. You can have, but it can be decomposed into periodic into Fourier modes. But it does not imply that you have a periodic sequence.
It can appear in different times, but the distribution will be the same. So they don't need to appear in the same order.
So the distribution is,
Yes.
okay.
The distribution is preserved. Okay, is this clear? Now, what we said about K, yes,
You said that we are satisfied with the weak stability when the mean is equal to the standard deviation. So where does the mean and the standard deviation?
we are going to get there.
Oh.
So the mean will be the mean flow, and the standard deviation in fluid dynamics will be linked to what we call turbulence intensity. Okay, but we are going to get there. First, let's look at the link between what I said about stationarity and what should be your expectation on the matrix K. What did we say about the matrix K? We said, it's not longer there. We said that K EJ is the correlation between the snapshot I and the snapshot J. Okay, so
Total correlation, so identity.
no, not identity. But what it means is that, for example, if I take the correlation 10-35, this should be the same as the correlation 20-45. Because the only thing that matters is the distance between them. Okay, so in terms of matrix, if you think about how the matrix is having its data, what you should have is that this becomes diagonally a circulant, it's a Toplitz's matrix. Okay, it should be, I should have constant values along all its diagonals, precisely because only the distance between them matters. Is this clear?
Can we determine this distance? Like, how do we know?
That's a good point. You usually don't. It depends on the time scale of your problem. It depends on the, usually in statistics, we will use the autocorrelation function to look for what is this distance in your process. It depends on, if you are, for instance, in the Gaussian process, it depends on how much your kernel, your covariance matrix is spiky or flat. Okay, if I have a covariance which is very flat, it means that what happens here has an influence to many more time steps coming afterwards. But if my covariance is very spiky, what happens here is soon forgotten after a few steps. There is no correlation. The autocorrelation dies quickly. Okay, so it depends on your process. But for the purpose of this example, what they have noticed is, and this is a very beautiful property, is that in the case of a stationary, this matrix should become Toplitz's. Now I'm going to ask you a very hard question. What are the eigenvectors of a Toplitz's matrix? It's very tough. Fourier modes. You can show, that's a beautiful thing to show, that if you take a Toplitz's circular matrix and you diagonalize it, you are back to the Fourier modes. You obtain all the roots of unity in the complex domain. And this was the observation that led this group to come out with this very beautiful idea. And the idea is the following. Okay, I look at my correlation matrix. It's not like this. What do? I push it to make it like this. So they come with a filter which is acting only along the diagonals. in which, because of stationarity and the fact that it has to be a topic circulant, they make it circulant. So I will take a slice. When this finishes here, I will start over in the other time step. So I will build a filter which is circulant, okay, respecting the idea of stationarity. And I will try to, with this filter, to make my correlation matrix looks as much as possible as this. The more I do this, the more the eigenvectors of that, so the POD modes, will look like Fourier modes. Okay, so you have the code there. This will provide you with the matrix formalism, which is exactly the same, because you take K as you had with your POD, you filter it, and then the rest is just a normal POD, provided that you have filtered it with this diagonal filter. Okay. If we do it for this test case, and again, it's part of the exercise, as a parameter, so in Modulo, it is implemented with a Hamming kernel, and you have to decide, you need to know a bit about filtering. This is an FIR filter, where you decide the length of the filter and the cutoff of the filter. So the more you make this filter, let's say, strong, the more you remove the high frequency there, the more indeed the modes start to have a narrower frequency range, and the more you will converge towards Fourier. Fantastic idea. That's for stationary. Okay. Now you should say, well, but how do I know how much I should filter? There is no golden rule. It's again application dependent. And what is also difficult here is that there is no simple link between the filter that you're going to do and the modes that will come in terms of frequency boundless.
I think the question for the flow you showed here. How did you know that it is built as a stationary time series, or how did you know?
Good point. How do I check for stationary in this case? That's a very good point. In this case, I know it's stationary.
Yeah, that's
Okay, but in general, you can check for stationarity in various ways. One approach would be, for instance, to run to look for the mean, to make sure that the mean is not changing too much. To try to test this hypothesis. The hypothesis that the standard deviation is remaining constant over various chunks.
How do you choose this this period T? Is it
You mean this?
Yes, the period T that as we vary it, we can.
So this T you usually don't choose. This will come from your process. This you don't choose. But what you can choose is the width of this. This is a problem of sampling, in fact. Because you can say, okay, let's say that I have 20,000 snapshots. You should partition them into blocks that have enough convergence. How do I know that? Because you look at the mean. So I take 100 points, I look at the mean, 98. I take 200 points, I look at the mean, 98.001. Okay, so 100 points was enough, okay? And then you just flip it over and you check it that your moments are more or less preserved. Okay? More questions? So that is a beautiful tool. But again, there is the idea of stationarity involved. And now we go to the last tool, the MPOD. So I think I skip here a slide. Where does the MPOD come? The MPOD comes from the observation that if you look at the temporal correlation matrix, a K, without diagonalizing it, you have all the information there. It was just that the POD messed up because of its array to be optimal in the convergence. So what you're seeing here is the contour plot of the temporal correlation matrix of the cylinder test case. You remember the cylinder test case, high velocity, then you decrease the velocity. Okay. If we plot K, the contour of K, you will see something like this. So here I'm putting the reminder. In the first approximately 2 seconds, this is yellow, so the velocity was higher. Then it's getting lower. Okay, you remember, because of what we have seen here. So this matrix contains enough temporal information through the correlation of the various snapshots. But if we do the frequency transform, so the Fourier transform of that, we observe this. So this is now is the contour of the absolute value of the Fourier transform of K. Okay. Before I was looking at the information in time of K. Now I'm looking at the information in frequency of K. And if I look at the diagonal of that, you will observe this spectrum. Indeed, we have 303 Hertz was the first, the last transient, and 459 that was the other transient. Okay. What will generally happen is not mathematically proved thing, but something that will often happen is that the POD will put most of the spectral content that you have in the diagonal of K into the first modes. In fact, this was happening here. Okay, the second mode had a spectrum that was almost like this one. Okay. So what is the idea of the MPOD? Is the following. Okay, dear POD, do your optimality things, but let's keep some bounds. Okay. So in this case, let's partition that into blocks. Okay, a block with a one scale, another scale, third scale, fourth scale. Each of this block will partition my frequency domain into various parts. But carefully, because you're not going to do a filter like we did in the case of the SPOD. In the SPOD, you filter and what has been removed is being removed. Here we just partition. This is multi-resolution analysis. This is not filtering. So some of the frequency content goes to scale 4, some other goes to scale 3, some other goes to scale 2, and so on and so forth. Okay, we just split them. And then you have to build these filters respecting some criteria, which I will not detail too much. But the idea is that they have to be complementary. So they have to be a partition of unity to make sure that nothing is lost. What I'm removing to scale 3 is being given to the others, you see, so that they are all complementary. So the diagonal have to be 1, and there should be no overlapping. Okay, the filter in scale 1 has no common element with the filter of scale 2. And if you do this, what you can show is that now you have, say, 4 scales, 5 scales. You can look at the covariance matrix at the famous K at each scale. So filtered on each scale. If your filter is done nicely, you have preserved all the key properties of this matrix K. It's still symmetric, positive, definite. It still has the thing that it needs to have. So it will have its own PODs. Now, as before, we will have many PODs, okay, for each scale. And what is beautiful is that the PODs of the various scales are mutually orthogonal if you filter the things well. Okay, so the POD modes of scale 1 are orthogonal to the POD modes of scale 2 or scale 3 and so on. So once you have done all of that, we can reassemble and put together all these modes, all these POD modes of the different scale together to form one single basis, which is orthonormal. Okay, and that is the MPOD. It's clear? So it is like a POD, if you want, which has been additionally constrained to some range of frequencies. But again, we're not throwing away any information, we're just redistributing the information. So if mode 1 has a low frequency, should not have also high frequency there. Okay. This is the way you implement it in Modulo. You need to give, this is the most important information, is the frequency splitting vector that tells you how you're going to do this repartition. Okay, so here we will take from 0 to 10 Hertz, from 10 to 290 Hertz, and so on and so forth. Okay, and then the last is going to be from 470 until Nyquist frequency. So in this case, 1500. Okay. Then you have two parameters. So this one collects the length of the FIR filters that will be used in each block. And this lets you decide if you want to use the MPOD as a filter or not. If you put 0, that scale will be killed. And then the MPOD becomes also a filter. Okay. If you put 1, that scale will be kept. If you do this for the cylinder test case, here's what is happening. The first mode, if you compare it with the POD1, has a much smoother evolution, which is capturing really the large scale. No high frequency on that, or very little. No filter is perfect in this world, but keeping only the low frequency part. Then, if I look, for example, at the second mode, it will pick a very narrow range of frequencies, which was associated to that shading. It will have also time localization. It will tell me that mode was active until 1.5 seconds and then switched off. So you have frequency localization, time localization, space localization through the mode. You remember the convergence of the POD was 1, 2, 3, 0. Now we have partitioned a bit more, so you have 1, 2, 3, 4, 5, 0. So we are losing a bit on the convergence, but not that much. Okay. And guess what will be the other modes? Pick the other frequency, pick the other time localization, and tells what was the other thing happening.
Concerning the orthogonality, it's like POD, so
Very good question. So concerning the orthogonality, we will guarantee the orthogonality of the psi, but we cannot guarantee the orthogonalities of the phi's. Okay. For me, having the orthogonality of the psi's is already a luxury. Having also the orthogonality of the phi, this is only POD can do. There is no other decomposition that can have both of them orthogonal.
the size would be,
The psi's will not be orthogonal.
the size would be about the 5.
Sorry, the psi's will be orthogonal by construction, but the phi's will not be orthogonal in the MPOD. Okay, but you can see that the lack of orthogonality in the phi's for this case, it's so small that a little QR will re-put them back without too much effort. You see?
So, go back to the question of Galerkin projection.
Fantastic question. Taken as it is, as it comes, I will not, because I don't have the orthogonality on phi.
That size,
Yeah, but those are the ones that we're going to solve for. You saw when we did the Galerkin on the cylinder, we were solving for the A's that contained the psi's. You see? The orthogonality of the psi's is very helpful to build the phi's quickly and without too much computational cost. But then if the phi's are not orthogonal for Galerkin projection, it's not very good. What I can tell you by experience is that the loss of orthogonality of these guys is very little. And this is why the MPOD gets very close to the POD, because the loss of orthogonality is little. Otherwise, you will not be able to be that close to the POD, you see? There is no free lunch if you want to have the spectral independency, so you're putting constraints onto the POD. The price to pay will always be a loss of convergence, which will manifest as a loss of orthogonality. So if then you want to use the MPOD to do the Galerkin projection, you have to be careful, maybe realigning a bit the modes with a QR, as we did also in the first exercise.
So just to wrap it up, what you do is you get your K matrix, right? And then you take it to the Fourier space, you look at the diagonal and that gives you your spectrum. And then you put on the filters and that gives you your...
Exactly, you partition, and then you will have a constrained POD. Keeping in mind that the only control that you have is on how you partition that. But then that the first MPOD mode is belonging to that scale or that another scale. This is not your choice. This will still come from the MPOD. Okay.
But why is it that this diagonal is picking up the
leading frequencies? Because that diagonal you can show is that is the spectra of the autocorrelation. So it's really, most of the time that will be, if you take this plot and you compare it with the plot of a DFT sigma versus frequency, you will see almost the same stuff. And if you look at the frequencies of the leading POD modes, it will also be the same stuff.
But that's just observational, right?
Yes, I don't have any mathematical demonstration of that. But what I usually do, I look at the spectra of the matrix. If I don't see like multiple peaks or like clearly, like in this case, you had clearly multi-scale patterns, POD is just fine. But if I want to split and have this additional degree of freedom in selecting the ranges of frequencies, then you go for the MPOD.
It's like your wavelet in the POD wave space.
Exactly. In fact, the first formulation of the MPOD was done with wavelets. You can show that this repartition of scales can be done with wavelets. Here it's done through a filter banks, which is a generalization of the wavelets. More questions? So the other thing that I wanted to show you was this. So remember, 50 DFT modes, 22.8%, 3 POD modes, 15%. Okay. 5 MPOD modes, we are more or less competing with the POD. And if we will pick 6 modes or 10 modes, they will be basically the same, because the old modes that comes after the 5 or 6 are nearly 0, so they don't count. So when I say that the POD cannot be, you cannot do better, I mean for an equal number of modes, because otherwise you can also be equal. In this case, if I stop at 10 modes, they are comparable, MPOD. But if I stop at 3, no, they cannot be comparable. Okay. So I will wrap up the entire course, if you want, with some take-home messages, let's say. If you are focusing on just compression, you just want to have the strongest possible compression, you want an orthogonal basis in one shot, because maybe then you want to do Galerkin, etc., etc. The POD is your tool, and there is no discussion about that. If you are looking for quasi-linear dynamics, what is a quasi-linear? Something that can be correctly easily represented with exponentially increasing or decreasing sinusoidals. For example, departures from a stability. You have a mean flow and then it's departing towards another state. But if you have like departing from a state, saturation, and then maybe something else, no, this cannot be described by a linear dynamics, okay? So if your problem can be described by a quasi-linear dynamic, maybe you are doing stability analysis, things like that, the DMD is your tool. If you're looking for harmonic patterns, frequencies like oscillatory behaviors, and your data set is too noisy and you don't trust too much the DMD that might not hold in such a presence of noise and in more complex dynamics, then I will say the SPODs are your tool. Both tools for stationary data set, I should have added for stationary data set, are really the way to go. Okay. If you want some more flexibility to say, I want to have some localization in frequency, in space and time, want to have the full, let's say, command, then the MPOD will be your tool. And as I was saying, all the composition can be used as a filters. You can always have a DFT and then kill some modes, or do the POD and then kill some modes. They can all be used as a filters. But the advantage of the MPOD is that you have two things at once. You have a filter that goes both in the frequency and in the correlation domain. On the other hand, the POD can have spectral mixing, but if you're looking for some specific patterns, better go for the MPOD in this case. The DMD very often will lead to problems. Consider first a quick and dirty DFT just to have a first idea of what are the coherent patterns, the harmonics there. And the MPOD, it's a beautiful tool, but you need to select carefully all the parameters of the filters. You need to know a bit about filterings when you set their length, their orders and stuff like that. So it requires a bit of knowledge about filtering. Okay. With that, I think we can close. There was an exercise and you have the data to download the JET and to do the MPOD. Try it also on your test case if you have your data set that you want to play with. But with this, I think I will close.
Just on time.
Perfectly on time. Do you have questions? No? Understandable. Understandable. Then, okay, we can call it a day.
Thank you again.
Thank you.
I think that was a very good use of 2 days. Like no one could have compressed this much material with this much efficiency. So really, thank you, Miguel, for doing this. For flying all the way from Brussels to be with us. And I think this is just a start, and we hope to get the collaboration going. We already are collaborators, but you guys can start reaching out, and you now have a reference in the field.
Thank you. It was very nice. I mean, I really enjoyed a lot. And you all had very good questions, and I mean, it was very nice. Good, guys. So enjoy the codes. You have a lot of material there, much more than what I actually covered. So play with that. And if you have questions or things, my email is in almost all the slides. So okay.